The blockchain is a term that has come to mean many things to many people. For developers, it is a set of protocols and encryption technologies for securely storing data on a distributed network. For business and finance, it is a distributed ledger and the technology underlying the explosion of new digital currencies. For technologists, it is the driving force behind the next generation of the Internet. For others, it is a tool for radically reshaping society and economy, taking us into a more decentralized world. Whichever way you look at it, blockchain has become a term that captures the imagination and fascinates many, as the implications of such technology are truly profound. For the first time in human history, people anywhere can trust each other and transact within large peer-to-peer networks without centralized management. Trust is established not by centralized institutions, but by protocols, cryptography, and computer code. This greatly strengthens our capacity for collaboration and cooperation between organizations and individuals within peer networks, enabling us to potentially form global networks of collaboration without centralized formal institutions. Unprecedented, but hugely relevant in an age of globalization and a new set of 21st century challenges that require mass collaboration. The blockchain is a complex technological, economic, and social phenomenon. It calls into question what might have seemed to be established parameters of the modern world like currency, economics, trust, value, and exchange. To make sense of this, one needs to understand it in a holistic context all the way from its technicalities to its aspirational potential. This course is designed to do exactly that, by giving a 360-degree overview to the different dimensions of the technology, its potential application within various industries, and its far-reaching implications for society and economy. In the first section of the course, we give an overview to the blockchain both on a technical and non-technical level. We also discuss the importance of the blockchain within the context of the emerging next-generation Internet. In the second section, we talk about the blockchain as a so-called trust machine and how it enables transparency and collaboration. We will look at distributed ledger technology, talking about smart contracts, Ethereum, and decentralized applications. In the third section, we introduce you to the workings of token economies, illustrating how the blockchain and distributed ledgers can work to build vibrant ecosystems through the use of tokens to incentivize behavior. In the last section of the course, we will be looking at specific applications of the blockchain to economy, society, technology, and environment, looking at both existing practical applications and potential future applications. The blockchain is a so-called emerging technology that is currently experiencing very rapid evolution. Within the space of just 2 or 3 years, it has already gone through changes in its technical implementation and our understanding of what it is and can be. As such, our aim is to future-proof this course by not dwelling excessively on existing technical implementations, but presenting a more conceptual understanding of the blockchain within the broader process of change of the emerging next-generation Internet. The blockchain is much more than a technology. It is also a culture and community that is passionate about creating a more equitable world through decentralization. It is a movement to disrupt the disruptors, to redesign the Internet, and in so doing, shake up existing centralized incumbents. Throughout the course, we will introduce you to this culture and its aspirations. This course is non-technical in nature. It is an introductory course, and thus all terms will be explained. It should be accessible to anyone with a basic understanding of web technologies and economics.
In this video, we're going to give a high-level overview looking at the primary dimensions of this technology that we call the blockchain. We'll first talk about the underlying technology, then the distributed ledgers that this technology supports, then the token economies that can be built on top of that ledger system. We'll only touch upon these topics here to get an overview before going into them in more detail in future videos. On its most basic level, the blockchain is a new class of information technology that combines cryptography with distributed computing. both of which have existed for a number of decades. It was the genius of Satoshi Nakamoto to combine them in new ways, to create a model where a network of computers collaborate towards maintaining a shared and secure database. As such, we can say the blockchain as a technology is simply a distributed, secure database. This database consists of a string of blocks, each one a record of data that has been encrypted and given a unique identifier called a hash. Mining computers on the network validate transactions, add them to the block they're building, and then broadcast the completed block to other nodes so that all have a copy of the database. Because there is no centralized component to verify the alterations to the database, the blockchain depends upon a distributed consensus algorithm. In order to make an entry onto the blockchain database, all the computers have to agree about its state, so that no one computer can make an alteration without the consensus of others. Once completed, a block goes into the blockchain as a permanent record. Each time a block gets completed, a new one is generated. There is a countless number of such blocks in the blockchain, all connected to each other, like links in a chain, in proper, linear, chronological order. The blockchain was designed so that transactions are immutable, meaning they cannot be deleted. Each block contains a hash value that is dependent upon the hash of the previous block, so they're all linked together, meaning if one is changed, then all the other blocks linked to it going forwards will be altered. This works to make the data entered tamper-proof. What we've described here is the workings of the first generation of blockchains, which function largely simply as databases. But the technology is currently evolving to become much more than this, as the second generation already provides the capacity to execute any computer code on the blockchain. The system is evolving to become a globally distributed cloud computing infrastructure, and as we'll discuss in a future video, it remains very much a work in progress when seen from this perspective. Blockchain technology works to create a permanent and secure database. This makes blockchains suitable for the storage of a record or transaction that involves value or in some way needs to be a secure and trusted source of information. These secure, distributed records are called distributed ledgers. A distributed ledger is a consensus of replicated, shared, and synchronized digital data geographically dispersed across multiple sites, countries, or institutions without centralized administration or centralized data storage, being maintained instead by a distributed network of computers. Such ledgers can be used for any form of asset registry, such as inventory or monetary transactions. This might include the recording of hard assets such as physical property, cars, homes, etc., or intangible assets such as currencies, patents, votes, identity, healthcare data, or any other form of valuable information. This distributed ledger technology enables us to replace a multiplicity of private databases within each organization with one shared database that is trusted and accessible by all parties involved. In this respect, the blockchain enables trust between parties that may otherwise not trust each other. The results greatly strengthen our capacity for collaboration between organizations or between individuals peer-to-peer, without dependency on third-party centralized institutions. Likewise, they result in transparency and many other efficiencies. This is of major significance, as we currently have many centralized organizations that may be internally optimized, but the inter-organizational space in between them is really inefficient, with huge amounts of border friction, redundancy, arbitrage, and resources wasted on competition. By enabling trusted inter-organizational networks, these ledgers enable the formation of organization and collaboration where previously there was none, such as across whole supply chains, or for different healthcare providers to collaborate around the patient's needs, or for different transport providers to collaborate in delivering an integrated logistics network. Likewise, second-generation blockchains offer the possibility to automate the workings of these networks through what we call smart contracts. Smart contracts are computer code that is stored inside a blockchain, which encode contractual agreements. These smart contracts are self-executing contracts, with the terms of the agreement or operation directly written into lines of code, which are stored and executed on the blockchain. Like normal computer programs, these containers hold algorithms that take an input of data and, depending on the value of the input, trigger certain events. For example, this might be a financial contract that takes as the input the amount of money in a person's account. If it is above a certain level, then it increases the interest rate that they earn on their deposit. Such smart contracts can be used for automating many basic operations on the network, once again working to remove the need for intermediary third-party institutions, as smart contracts can be trusted, are tamper-proof, and execute automatically. Much of the current discussion surrounding blockchain remains at the level of the technology and the possibilities of distributed ledgers, as a shared, trusted database enabling the collaboration between organizations, with the resulting disintermediation of centralized institutions and market exchanges. However, its implications go far beyond this, as the blockchain concept is more than just a database or ledger. It is a new organizing paradigm for the discovery, validation, and transfer of all discrete units of value, and the development of distributed organizations via token market systems. A token is a quantified unit of value that is recorded on the blockchain. This value may be of any kind. It may be likes on social media, it might be a currency, it might be the integrity of an ecosystem, or it might be an electrical unit. Token networks consist of a network of independent nodes that act autonomously, but through incentive structures and the signaling system of the market, self-organize to create emergent coordination, and thus a distributed management system. For example, we might create a clean air token, where anyone who provides a service that contributes to the maintenance and provision of clean air can earn tokens, for example by planting a tree, while those who pollute, by say operating a combustion engine, have to pay in air tokens. Thus, instead of having a centralized authority and a Clean Air Act, we have a token market that works to create signals that align people's incentives with maintaining and growing the underlying resource. Likewise, this same model could be applied to the management of technology infrastructure. As an example, we could think of traffic control. We currently have traffic control systems in cities whose operations are monitored by centralized control centers. But in a world of autonomous vehicles on the blockchain, cars could signal to each other, peer-to-peer, bidding tokens to see which gets priority. In such a way, the system has dynamically allocated resources and self-organized via distributed token networks. In short, blockchain is not just an information technology, but also an institutional technology, in that it enables us to design incentive structures in the form of token economies, and in such a way convert centralized organizations into distributed markets via token economics. This is where things start to get quite complex, as we move into the realm of designing economies and incentive systems for coordinating human activity in a decentralized fashion, something that could potentially enable the coordination of human activity at a much larger scale than has been possible before. The great design innovation of the blockchain is really its capacity to coordinate a network of autonomous nodes towards maintaining a shared infrastructure, and this is done not just through innovations in information technology, but also through the design of incentive systems, which has traditionally been the domain of economics. Through adding a layer of trust and value exchange to the internet, the blockchain merges our newly developed information networks with the institutional structures that sit on top of them. In so doing, it greatly strengthens the capacity of those networks as a new mode for organizing society and economy. By merging economics and technology, it enables us to redesign institutional structures and ultimately reconceptualize how we organize virtually every aspect of society, economy, and even technology infrastructure, based on networks of autonomous nodes that are incentivized to collaborate. Of course, it does not do this alone. Such claims can only be realized in combination with other technologies and broader processes of change. As such, the blockchain has to be understood in the context of a broader set of technological transformations taking place with the current evolution of the internet. Most notably, much of what the blockchain promises will only be possible given parallel developments in the Internet of Things, datafication and advanced analytics, all of which are combining to form the next generation of internet, of which the blockchain will be a critical infrastructure. In this video, we're going to talk about the basics of the blockchain as a technology. On its most basic level, the blockchain can be understood as a new kind of database, at least this was its original design. What's different about this database is that it's distributed. Digital databases have been around for a while now, but until recently they've been designed to centralize information on one computer or within one organization. The blockchain, though, uses a distributed network of computers to maintain a shared database. The blockchain is then a set of protocols and encryption methods that enable a network of computers to work together in securely recording data within a shared open database. This database consists of a series of encrypted blocks that contain the data. The blockchain is a continuously growing list of these blocks of data, which are linked and secured using cryptography. This makes it a trusted database, with this trust being maintained by open, secure computer code and encryption instead of any single institution. The database stores information in blocks that are linked together through hash values, with entries to this database being made by computers that all have a copy of the database and all must come to consensus about its state before they can update it. So these are three central concepts to understanding the system's workings: that of blocks and hashing, mining and proof of work, and distributed consensus. We'll go over each of these separately. In terms of its structure, a blockchain may be considered as a series of blocks of data that are securely chained together. New blocks are formed as participants create new data or wish to update existing data. These blocks are encrypted and given a hash value that represents a unique identifier of the data within that block. This hashing works by a standard algorithm being run over the block's data to compress it into a code, which is called the hash, which is unique to that document. No matter how large the file or what information is contained, it is compressed into a 64-character secure hash. This hash value can be recalculated from the underlying file, confirming that the original contents have not changed, but the reverse is not possible. Given just the hash value, you cannot recreate the block's data contained within it, which is encrypted. All blocks of data which are formed after the first block are securely chained to the previous one. This means that the hash value of the next block in the chain is dependent upon the previous one. Thus, once recorded, the data in any given block cannot be altered afterwards without the alteration of all subsequent blocks. As well as this hash pointer linking to the previous block, each block typically contains as well a timestamp so that we know what happened and when it happened. This hashing and linking of blocks makes them inherently resistant to the modification of their data, making them immutable records. You can only write data to the database, and once it's there, it's very hard to change, almost impossible. Thus, data stored on the blockchain is generally considered incorruptible. Blockchain security methods include the use of what we call public key cryptography. A public key, which is a long, random-looking string of numbers, is an address on the blockchain. Value tokens sent across the network are recorded as belonging to that address. A private key is like a password that gives its owner access to their digital assets or the means to otherwise interact with the corresponding data. A public key is associated with the private key so that anyone can make an encrypted transaction to the public key address, but that encrypted message can only be deciphered with the private key that corresponds to that public key. In such a way, effective security only requires keeping the private key private. The public key can be openly distributed without compromising security. For example, on the Bitcoin blockchain, to receive funds from another person, you use a piece of software called a wallet, which creates a public key that you give to someone else for them to send Bitcoins to that address. With your corresponding private key, you can then access that address with those Bitcoins on it. The blockchain is a distributed system. This means there is no centralized organization to maintain and verify the entries on the database. This database is instead maintained by a large number of computers that are incentivized to provide computing resources by earning some form of tokens in exchange. But these computer nodes in the network themselves cannot be trusted individually. Thus, it is required that the system provide a mechanism for creating consensus between scattered or distributed parties that do not need to trust each other, but just need to trust the mechanism by which their consensus has been arrived at. Any computer that is connected to the blockchain network and using a client can perform the task of validating and relaying transactions. Each of these so-called minor computers gets a copy of the blockchain, which gets downloaded automatically upon joining the network. When new entries into the database are made, these changes are automatically broadcast across the network. Mining nodes validate transactions, add them to the block they're building, and then broadcast the state of the complete block to other nodes on the network. In order to randomize the processing of blocks across the nodes, and to avoid certain service abuses, blockchains use various time-stamping schemas, such as proof of work. Proof of work describes a system that requires a certain amount of resources or effort to complete an activity. Typically, this resource is computing time. As in the case of the Bitcoin blockchain, this is realized on some form of challenge, such that no one actor on the network is able to solve this challenge consistently more than everyone else on the network. Miners compete to add the next block in the chain by racing to solve a very difficult cryptographic puzzle. The first to solve the puzzle wins the lottery. As a reward for his or her efforts, the miner receives a small amount of newly minted bitcoins and a small transaction fee. A consensus algorithm, like Bitcoin's proof of work, functions to ensure that the next block in the blockchain is the one and only version of the truth, and it keeps powerful adversaries from derailing the system. Blockchains are trying to create a secure, trusted, shared database, and they do this through encryption and hashing, proof of work, and network consensus. The hashing and linking of blocks makes it difficult to go back and change a previous block once it's entered, but this alone would not be suffice to ensure that the data is truly tamper-proof. So then the proof of work system intentionally makes it computationally more difficult to alter the database, thus making it extremely difficult to alter all the blocks. On top of this, it places a distributed consensus mechanism, so that even if someone did manage to do this, their record would not match that of others, and thus would not be accepted as a valid record. So to successfully tamper with the blockchain, you would need to alter all the blocks on the chain, redo the proof of work for each block, and take control of more than 50% of the peer-to-peer network. Only then would your altered block become accepted by everyone else. On a blockchain of almost any size, this would be almost impossible to do. Indeed, the Bitcoin blockchain is very good proof of this, given that it now secures hundreds of billions of dollars using this method, without the network having yet been compromised. At the end of the day, what this technology enables is a database that is secure with automatic trust that is enabled by open source code and encryption. The data is tamper-proof. Once information is put into the database, it cannot be altered afterwards. It is a shared database, as many people across the network have a copy which is continuously being updated so that all have a single source of truth. Likewise, it is transparent, meaning that everyone can see all of the transactions and alterations made to the database if needed. Data quality and the resilience of the network is maintained by massive database replication across many different nodes on the network. No centralized official copy exists, and no user is trusted more than any other. Having started out life as simply a mechanism to enable Bitcoin, it has become increasingly recognized that this system is secure enough to work as a ledger for the recording and exchange of any value, what we now call a distributed ledger. Over the past years, blockchain has been evolving fast, from the original Bitcoin protocol to the second generation Ethereum platform, to today, to where we're in the process of building the third generation of blockchains. In this evolution, we can see how the technology is evolving from its original form as essentially just a database, to becoming a fully fledged, globally distributed cloud computer. In this video, we're going to trace the past, present, and future of blockchain technology. The first blockchain was conceptualized in 2008 by an anonymous person or group known as Satoshi Nakamoto. The concept and technicalities are described in an accessible white paper termed Bitcoin, a peer-to-peer electronic cash system. These ideas were then first implemented in 2009 as a core component supporting Bitcoin, where it served as the public ledger for all transactions. The invention of the blockchain for Bitcoin made it the first digital currency to solve the double spending problem without the need of a trusted authority or central server. It was only later that we came to really separate the concept of the blockchain from that of its specific implementation as a currency in the Bitcoin. We came to see that the underlying technology had a more general application beyond digital currencies in its capacity to function as a distributed ledger, tracking and recording the exchange of any forms of value. The Bitcoin design has been the inspiration for other applications and has played an important role as a relatively large-scale proof of concept. Within just a few years, the second generation of blockchains emerged, designed as a network on which developers could build applications, essentially the beginning of its evolution into a distributed virtual computer. This was made technically possible by the development of the Ethereum platform. Ethereum is an open-source, public, blockchain-based, distributed computer platform featuring smart contract functionality. It provided a decentralized, Turing-complete virtual machine, which can execute computer programs using a global network of nodes. Ethereum was initially described in a white paper by Vitalik Buterin in late 2013 with the goal of building distributed applications. The system went live almost 2 years later and has been very successful, attracting a large and dedicated community of developers, supporters, and enterprises. The important contribution of Ethereum as the second generation of blockchains is that it worked to extend the capacity of the technology from primarily being a database supporting Bitcoin to becoming more of a general platform for running decentralized applications and smart contracts. both of which we'll discuss in coming videos. As of 2018, Ethereum is the largest and most popular platform for building distributed applications on. Many different types of applications have been built on it, from social networks to identity systems, to prediction markets, and many types of financial applications. Ethereum has been a major step forward, and with its advent, it has become ever more apparent where we're heading with the technology, which is the development of a global distributed computer, a massive globally distributed cloud computing platform on which we can run any application at the scale and speed of today's major websites, with the assurance that it has the security, resilience, and trustworthiness of today's blockchains. However, the existing solutions that we have are like extremely inefficient computers. The existing blockchain infrastructure is like a really bad computer that is not able to do much except proof of concepts. Getting to the next level remains still a huge challenge that involves some original and difficult computer science, game theory, and mathematical challenges. Scalability remains at the heart of the current stage in the journey that we're on, and this is what the third generation of blockchain technologies are trying to solve. The mining required to support the Bitcoin network currently consumes more energy than many small nations, being equal to that of Denmark and costing over $1.5 billion a year in electricity. A lot of this is being fueled by cheap but dirty coal energy in China, where almost 60% of the mining is currently being done. This high energy consumption is simply not scalable to mass adoption. Ethereum and Bitcoin use a combination of technical tricks and incentives to ensure that they accurately record who owns what without a centralized authority. The problem is, it's difficult to preserve this balance whilst also growing the number of users. Currently, blockchain requires global consensus on the order and outcome of all transfers. In Ethereum, all smart contracts are stored publicly on every node of the blockchain, which has its trade-offs. The downside is that performance issues arise in that every node is calculating all the smart contracts in real time, which results in low speeds. This is clearly a cumbersome task, especially since the total number of transactions is increasing approximately every 10 to 12 seconds with each new block added. The volume of transactions is likewise an existing constraint. With cryptocurrency, speed is measured by TPS, transaction per second. The Bitcoin network theoretical maximum capacity is up to 7 transactions per second, while the Ethereum blockchain, as of 2018, can handle about 15 transactions per second. By comparison, a credit card network is capable of handling more than 20,000 transactions per second. Equally, Facebook may have about 900,000 users on the site in any given minute, meaning that it's handling about 170,000 requests per second. Another issue is that of cost. The fact that it costs some small amount to run the network, so as to pay the miners for maintaining the ledger. What we have is okay for a limited number of large transactions, such as sending money, but making a small transaction, like purchasing a coffee, could not be done by most blockchains. They simply can't, in their existing form, deal with a very large amount of microtransactions, such as would be required to enable high-volume machine-to-machine exchanges. It would prove too expensive to operate these kind of economies that involve many small exchanges. But this is exactly what many people will want to use the blockchain for in the future. In response to these constraints, a third generation of blockchain networks are currently under development. Many different organizations are currently working on building this next generation blockchain infrastructure. Such projects include Definity, Neo, EOS, IOTA, and Ethereum itself. They're each using different approaches to try and overcome existing constraints. Going into the details of how these different networks work is a bit advanced for this course, so we'll just give a brief overview to 2 of them. The Lightning Network is one such project that seeks to extend the capacities of existing blockchains. The main idea is that small and non-significant transactions do not have to be stored on the main blockchain. This is called an off-chain approach because small transactions happen off of the main blockchain. It works by creating small communities wherein transactions can take place without each of those transactions being registered on the main blockchain. A payment channel is opened between a group of people with the funds being frozen on the main blockchain. Those members can then transact between each other using their private key to validate the transactions. This is a bit like having a tab or an IOU with the shop, where you just mark down what you've exchanged so that you don't have to update the main record in the bank each time you make a purchase. The record stays local between the members involved, before at some time settling the finances and updating the main bank record. This only requires 2 transactions on the main blockchain, one to open the transaction channel and one to close it. All other transactions happen just within the network, without it being registered on the main blockchain. This both reduces the workload on the main blockchain and makes it possible to run many very small transactions within the sub-network. As of the start of 2018, there is a proof of concept running live on the Bitcoin testnet, but the system will not be fully operational until later in the year, as is the case with most of these projects. IOTA is another example, whereas existing blockchains are sequential chains where blocks are added in a regular, linear, chronological order. The data structure of the IOTA system is able to achieve high transactional throughput by having parallel operations. The data structure is more like a network rather than a linear chain, wherein processing and validation can take place alongside each other. The other big difference is that there are no specialized miners in this network. Every node that uses the network functions as a miner. In the IOTA network, every node making a transaction also actively participates in forming the consensus. That is to say, everyone does the mining. This means that there is no centralization of mining within the network, which is what creates bottlenecks and demands lots of energy. Likewise, with this network, there are no transaction fees for validation, and with IOTA, because it is more user-generated, the more people that use the network, the faster it becomes, which is the opposite of existing systems, and obviously makes it very scalable. There are lots of other possible approaches to overcoming existing constraints, but suffice to say, the blockchain should be understood as an emerging technology, whose existing implementation is like a large-scale proof of concept, running on a very inefficient system, but through lots of experimentation and iteration will hopefully in the coming years evolve into this global distributed computer. As Melanie Swan writes in her book, first there was the mainframe PC, personal computer paradigms, and then the internet revolutionized everything. Mobile and social networking were the most recent paradigm. The current emerging paradigm for this decade could be the connected world of computing relying on blockchain cryptography. To understand this better, in the next section, we're going to talk about the blockchain in the context of the broader technological changes that are currently underway as we build the next generation of the internet, what we call the decentralized web or Web 3.0. How we understand the blockchain and where we are with it today is extremely transitory. In this respect, what we're talking about in this course when we talk about the blockchain is really this emerging IT infrastructure of a distributed global cloud computer. The next generation of blockchains will take us a step further on that journey. What we call the blockchain today is really just a very limited and often very inefficient version of this. We still have many very difficult problems to solve before we'll get there. Possibly that end state will look something like the blockchain of today, but possibly it will look very different. People will make big claims about the potential of the blockchain to revolutionize the foundations of social and economic organization, but the blockchain can only have such potential as part of a broader ecosystem of technologies that are emerging as the next generation of the internet, what may be called Web 3.0 or the decentralized web. Today, powerful technological changes are coalescing to take us into a new technology paradigm. These include the rise of advanced analytics coupled with datafication and the Internet of Things. The blockchain will have to work synergistically with these if its true capacities are to be realized. But to understand this next generation web, we need to understand a bit about the history of the Internet. Going back to the early 90s, Web 1.0 was the first generation of the World Wide Web. It was based primarily on the technology of HTTP, which worked to link documents on different computers and make them accessible over the internet. HTML was then used to display these documents so that any connected computer with a browser could access and read a web page. This first iteration of the web was all about information, as it enabled us to exchange information much more efficiently, and hence it got the name Information Superhighway. Even though it was a revolution in information exchange, content creators were few, with the vast majority of users simply acting as consumers of content. It was really very static and lacked interactivity. Whereas in the Web 1.0 era, people were limited to passive viewing of content. With Web 2.0, websites allowed users to interact, collaborate, and become the creators of content. With Web 2, people could not only read from the web, but also write to it, and thus it got the nickname the read-write web. By the early 2000s, new server-side scripting technologies such as PHP enabled developers to easily build applications where people could write information to a database, with that information then being dynamically updated every time they refreshed a page. Almost all of the websites that dominate the web today are based on this server-side scripting technology. It gave us social networking, blogging, video sharing, eBay, YouTube, Facebook, and all the other large platforms that most people spend most of their internet time using. The idea of Web 3.0 has been around for a while, but it's only very recently, with the development of the blockchain, that it has actually started to become something real. Web 2.0 has evolved to become highly centralized around very large platforms running out of ever larger data centers, creating many issues surrounding security, privacy, control, and concentration of power in the hands of large enterprises. It's only today that these issues are starting to enter into mainstream discourse. Web 3 is set to disrupt this whole technology paradigm, as the critical change that is coming about is that we're decentralizing the web. The blockchain provides the protocols and cryptography for a globally distributed network of computers to collaborate on maintaining a public, secure database. And with a virtual machine like Ethereum, we can run code on this, creating a new set of distributed applications. These new technologies of the blockchain, IPFS, and the distributed web enable us to reconfigure the internet into a distributed global computer, so that we're no longer dependent upon the web platforms and data centers of Web 2.0 to run the internet, but now can build and run applications on this shared global computing infrastructure. As Mike Leopold of the Institute for the Future noted, it starts with the realization that the internet that we know today is only one possible interpretation of the original vision of an open, peer-to-peer network, independent of any centralized technology, commercial entity, or sovereign government. Think of it as a first curve internet, one that is increasingly vulnerable to abuse and even collapse. To date, we've largely taken the infrastructure of the internet for granted. All of the innovation and action has been focused on the application layer that sits on top of it, on web applications like social networking or e-commerce. With the development of blockchain, and particularly with this third generation, we're starting to innovate on the low-level protocols, asking not if we can build a better web application, but if we can build a better internet. The implications of the decentralized web are indeed radical in that it enables us to create automated services, disintermediate existing incumbents, and enable people to set up their own secure networks of exchange, empowering them in new ways. The blockchain will be a core part of Web 3.0, but the next generation internet will also see the convergence of the Internet of Things and big data analytics. The ongoing, fundamental process of datafication will be a key aspect to this next generation internet. As we increasingly instrument our worlds, data will flow from all sources about everything. Datafication is the term given to our newly found ability to capture as data many aspects of the world and our lives that have never been quantified before. This process results in what we call big data. Vast amounts of unstructured data that can be mined by advanced analytical methods to gain new insight into the world around us. This is important with respect to the blockchain because firstly, it means we'll have a lot of sensitive data that we'll want to store. Secondly, we will be quantifying, accounting for and exchanging all sorts of value that we did not or could not in the past. Thirdly, such a diversity of sources of data combined with advanced analytics which can find cross-correlations and patterns within it, can provide a new source to verify the data that is being inputted to the blockchain without depending on a centralized authority for validation. The next generation internet will be much smarter. Whereas Web 1 was dumb and Web 2 was dynamic, Web 3 will incorporate various aspects of machine learning and cognitive computing as a service as it becomes infused into almost all applications, making the web truly adaptive, responsive and personalized. Whereas Web 1 and Web 2 were largely about people exchanging information, in Web 3, machines will come online and the internet will become something much more physical, as billions of devices and actuators connect it to all sorts of things, from tractors to watches to factories and drones, enabling them to interact and coordinate machine to machine. The value of the Internet of Things, IoT, will not be in making one device or system smart. It will be in enabling seamless processes across systems. This will require open networks that can communicate and coordinate components on demand across domains, organizations, and systems. The end vision of IoT is not to have our lives populated with thousands of smart things, but instead to change our world from discrete things to service processes. To do this, these technologies will have to communicate securely peer-to-peer, dynamically allocating resources, and this will require some kind of distributed, secure infrastructure like the blockchain, and likewise microeconomies. This ties in with the broader process of change which comes about as we move into a services economy called servicization, which is the shift from products and the ownership of things to the access of services on demand. For example, instead of owning a car, you simply have access to a car-sharing service. This economy of temporary usage via services requires the formation of frictionless markets and automated exchanges that the blockchain is well suited to support, as we'll discuss in a future video. These components of the next generation internet, the blockchain, the Internet of Things and advanced analytics, are each of them very powerful technologies that will have a profound effect on society. They will take us much further into this new world of the information age, as power shifts in a radical way from people in hierarchical institutions to automated networks and the algorithms that coordinate them. In the coming decades, more and more of our systems of organization will move to the internet, and it will become vastly more complex than today. In Web 1 and Web 2, we developed the internet from small to large through a client-server architecture that worked to centralize the web around large data centers. But the internet, after datafication and all these IoT devices have come online, will not be large. It will be more like infinite. You can get from small to large by centralizing, but you get from large to infinity through distributing. And that's what the blockchain can do for this next generation internet. Technologies are just tools that enable us to do things. The interesting part of the blockchain is really what it enables in terms of new forms of distributed organization. As one commentator noted, the blockchain is an institutional technology, not an information technology. There's an enormous difference between the two. Institutional revolutions are things that don't happen very often. Blockchain technology enables new forms of networked, distributed organizations, something that runs very much contrary to our existing organizational paradigm, and that's what makes it somewhat difficult for us to understand. The organizational model of the industrial age that we inherit today was one of centralization in order to achieve economies of scale through mass production, thus reducing unit cost and providing for a mass society. The technologies of the industrial age selectively favored centralization of production within closed, hierarchical organizations. Manufacturing is in centralized factories. Transport systems are centralized around transport hubs. Education within schools and universities. Entertainment centralized within mass media organizations. And governance centralized within state-run organizations, and so on. The information revolution is in the process of taking us into a new world of distributed networks as the organizational paradigm of the information age. The combination of telecommunications networks and computerized coordination enables us to replace centralized management within closed hierarchies with open networks. As the underlying technology matures, we're able to convert more and more systems that were previously closed and centralized and have them managed through automated networks, and the blockchain is just one more stage in this process. We saw this with the rise of the online platforms like eBay, Uber, or Alibaba, social networks, blogging, etc., that built massive networks of users exchanging goods and services. But these platforms were still dependent upon the centralized organization to manage the shared database, for the computing infrastructure, for the algorithms, for financial transactions, and to enable trust and authentication in the network. The decentralized web takes these platforms a step further by offering a shared, open and secure database that can be trusted by all parties, and a set of protocols for the secure exchange of value between organizations and individuals peer-to-peer. The web platforms are open networks. This means they do not just optimize within a given organization, but can enable coordination across whole industries. Indeed, this is why and how they're quickly supplanting the closed organizations. What centralized organizations enabled was trust, cooperation and coordination within organizations. But what the blockchain enables is trust, coordination and cooperation between organizations and between individuals. If we look at how our society and economy is currently organized, we'll see many closed organizations that are internally optimized. But when we look at the interorganizational space, it's extremely inefficient along many dimensions. If we look at the way businesses coordinate along a supply chain, or the way nation-states interoperate in the global political system, we will see there is huge redundancy and friction caused by discontinuities. A classical example of this is the border system between nation-states and the bureaucratic procedures for obtaining a visa for moving from one nation to another, which creates a massive amount of friction at the interorganizational space. And it's because those organizations don't have an effective interorganizational infrastructure for collaboration and coordination. This greatly reduces the overall effectiveness of these systems and the delivered outcome for the end user. When we look internal to these organizations, they look like efficient, well-oiled machines. But when we look between them, the whole space is very inefficient. The whole space is very ineffective at delivering overall outcomes. And this is part of the significance of the blockchain, because it provides a shared, trusted database between organizations. it has the potential to switch the dynamics within economy and society from competition between closed centralized organizations to collaboration between organizations, and greatly strengthen working capacities across organizational boundaries. The results of this would be much more efficient overall societal and economic outcomes. Indeed, we can note that achieving coordination across organizations could result in quantum leaps in delivering outcomes and our capacity to tackle major global challenges of today, such as environmental degradation, where weak existing inter-organizational institutional infrastructure has gained little traction. In this respect, the blockchain has the potential to give us not just incremental improvements, but an order of magnitude greater capacities within society through collaboration within whole ecosystems. It is precisely this coordination across organizations, industries, nations and people that is required to provide the resources needed to tackle some of today's most complex challenges, and it's precisely this that is significantly absent within existing institutional structures. Because of the centralizing forces prevalent within the industrial age, we live in societies that are operated by many different closed organizations, many different companies all producing cars and competing for market share, many different governments that all focus on the interests of their citizens over those of others, many different healthcare providers, transport providers, etc. The result of this is, though, a huge amount of inefficiency and redundancy when taken as a whole, many different companies all recreating the wheel within their own organizations and expending huge amounts of time and energy on trying to get ahead of their peers. We assume that this is the normal state of operations, that it's just human nature in some way. But in fact, it's really just a function of the institutional structures we have built over the past centuries. As game theory will tell us, people respond to the incentives and the socio-economic forces acting on them. In the absence of cooperative structures, competition is often the optimal strategy for individuals and organizations. But once there is the institutional structures to enable trust and coordination between members, cooperation can become a much more viable strategy for the agents involved. Because the blockchain enables this shared and trusted database that doesn't belong to any single organization, it makes it greatly more possible and viable for organizations to collaborate on a single solution or single source and achieve much better results for each organization and the economy as a whole. As an example of this cooperation across different closed organizations, we could think about the design and construction of a building. There may be many different companies involved in this process, all creating their own designs and diagrams for the building, with each having to continuously contact each other to access, exchange and cross-reference all this information. Given a single shared database, they could, though, all collaborate on a single design of the building, making for a greatly more efficient overall process, while at the same time each organization would benefit, and thus the overall results are more efficient. Likewise, the same is true for identity. We currently have many different copies of our identity spread across many different organizations, governments, social networks, employees, etc. But each of these only has a partial understanding of us. Currently, we're recreating the wheel for each organization, while data and reputation does not move well between them. Instead, a single identity could be created on the blockchain that belongs to the individual, with each organization then contributing to this data as they work together to create a more complete record of identity and reputation. In so doing, we've moved from all those frictions between these closed organizations to collaboration and synergies between them, creating something that is greater than any of the parts they had before. The same for a supply chain. Instead of each participant holding their own documents and records during each stage in the supply chain, a single record for the item could be created on the blockchain, with each organization then contributing their information to it, to create a single source of truth that is accessible to all as needed, while at the same time being more secure than having separate records in each centralized database. The end result of this new institutional technology is a much greater capacity for inter-organizational collaboration and powerful ecosystems that are greater than the sum of their parts. Given that all our current systems of organization that are centralized could be decentralized in this fashion using blockchain technology, we can see how it really could enable a reorganization of society and economy. Organizations within society rarely operate in isolation. They function as parts of ecosystems, and the value for society is not created by any one, but instead by the flow of value across the ecosystem. It's not Apple that delivers our iPhones, it's a massive global supply chain of hundreds of different organizations collaborating. Whereas our previous institutional structures optimize for individual organizations, the blockchain optimizes for the value within the whole ecosystem, and thus potentially much greater value for society as a whole. The information revolution is changing the world from disconnected to connected. The genie of hyperconnectivity is out of the bottle, and connectivity along virtually all dimensions is proliferating daily. As a consequence, our systems of organization will change from being based around fixed structures and boundaries to being coordinated via connections. Instead of the control of components through fixed hierarchical structures, organization will emerge out of the interaction and the exchange of value along those interactions. Enabling that will require a massive build-out of secure, frictionless information networks, this global cloud computer of the blockchain. To understand better how this shared database that enables inter-organizational collaboration works, we'll talk about distributed ledger technology. As we've been talking about, the blockchain is like another layer to the internet that enables secure, trusted records and transactions between people who may not otherwise trust each other. The trust is in the technology, computer code and mathematics, rather than people and centralized institutions. In this respect, people sometimes talk about the blockchain as a trust machine in its capacity to enable a network where trust is created by design. It's built into the system automatically. Because the blockchain creates a trusted database, it can function as a record of value storage and exchange. These records of value and transactions may be called ledgers. Since ancient times, ledgers have formed the backbone to our economies, to record contracts and payments for the buying and selling of goods or the exchange of assets like property. These ledgers started out as records in stone, clay tablets and papyrus, and later paper as they evolved into the ledger books supporting modern accounting. These ledgers enabled the formation of currencies, trade, lending, and the evolution of banking. Over the last couple of decades, though, these records have moved into the digital realm, as whole rooms of people working to maintain accounts have been replaced by digital computers, which have made possible the complex global economic system we live in. Today, this record-keeping system is once again being revolutionized, as these ledgers are shifting to a global network of computers, which is cryptographically secured, fast and decentralized, what we call distributed ledger or distributed ledger technology, DLT for short. A distributed ledger can be described as a ledger of any transactions or records supported by a decentralized network from across different locations and people, eliminating the need of a centralized authority. All the information on the ledger is securely and accurately stored using cryptography and can be accessed using keys and cryptographic signatures. Any changes or additions made to the ledger are reflected and copied to all participants in a matter of seconds or minutes. The participants at each node of the network can access the recordings shared across the network and can own an identical copy of it. At the same time, these networks make constantly available for examination a full audit trail of information history, which can be traced back to the moment when a piece of information was created, and every participant in the network can get simultaneous access to a common view of the information. These ledgers can be used for the recording, tracking, monitoring, and transacting of all forms of assets. All asset registries, inventories, and exchanges, including every area of economics, finance, and currencies. Physical assets such as cars and houses, and intangible assets such as votes, ideas, health data, reputation, etc. In this case, the blockchain can serve as a public record repository for whole societies, including the registration of all documents, events, identity, and assets. In this system, all property could become smart property. This is the notion of encoding every asset to the blockchain with a unique identifier such that the asset can be tracked, controlled, and exchanged on the blockchain. For example, distributed ledgers could be used to replace or supplement all existing intellectual property management systems, as they can register the exact content of any digital asset, such as a file, image, health record, or code, to the ledger and give it a unique identifier in the form of the hash values that we discussed earlier. There are two main classes of distributed ledger: public ledgers and permission ledgers. The former type is maintained by public nodes and is accessible to anyone. Bitcoin is a well-known example of a public blockchain where anyone can read the chain, anyone can make legitimate changes, and anyone can write a new block into the chain. Ripple is an example of a permission blockchain where the creators of the network determine who may act as transaction validators on that network. Distributed ledger platforms in each category have their own unique features. Some are designed for specific types of application, and others for more general use. For instance, in the Corda DLT platform, which is a consortium of more than 70 of the world's largest financial institutions, the sharing of individual ledger data is limited to parties with a legitimate need to know, which is not the case for public platforms. DLT technology can have a powerful disintermediation effect, as data can be put directly onto the shared database by the nodes in the network. There is no longer need for a centralized organization to provide this service. A developer can create a DLT on a blockchain and use public-private key cryptography to give people secure storage space on that ledger, allowing people to own their own data, which creates a very different scenario to the world we live in today. Currently, centralized organizations like Google and Facebook suck up all of the little bits of data we leave behind us and use it to serve us customized advertisements from which they create their revenue. This results in a huge power imbalance within society, where centralized organizations, armed with teams of mathematicians and computer scientists, use mountains of data to influence people's behavior towards purchasing the products of their advertisers. Data that is a very valuable asset in an information society and of critical importance to tackling major societal challenges is being used against us in many ways, creating a stumbling block that societies are becoming increasingly aware of. In a world of distributed ledgers, people have their own little databases on the blockchain and can own their own data, giving it to organizations to use when and where needed, fundamentally reversing the current dynamic and truly empowering individuals. Your health records reside in your health ledger, and different healthcare providers can access and update that single record, but only with the permission of the end user, as the data remains theirs, and they choose who can have access to it. Likewise, when people own their own data on a distributed ledger, they can transact directly peer-to-peer, as is the case with Bitcoin. With the existing traditional system, when you pay for a ride in a taxi with a credit card, it looks like you're paying the driver directly, when in fact, what is happening is that a database record belonging to my bank is being debited and a database belonging to the bank of the company that the driver works for is being credited. In this respect, we can note that in our society, value and data do not really belong to individuals. All the time, they're being held behind the walls of some centralized organization, and we are dependent upon them to secure and validate it, creating huge power imbalances within society. In contrast, with the Bitcoin blockchain, the individual has a ledger record and a secure key with which they can access their record. When they send money, they send it directly to the other person's record. It simply gets debited from your record and added to theirs directly, peer-to-peer. No centralized organization holds that data. Distributed ledger technology can greatly improve transparency, reduce corruption, and improve security while reducing overhead costs of auditing, accounting, and legal issues. Currently, records of value are hidden within the databases of centralized organizations, where they are largely inaccessible for their many possible uses within other systems. They are open to manipulation by members within those organizations, which breeds corruption. And because of that, there has to be all sorts of regulation and legal requirements that create many overhead costs. Added to this, they are centralized points of failure for critical data sources, as large concentrations of valued data prove very attractive for malicious actors. Likewise, it is inefficient to be constantly updating and synchronizing data across many centralized databases. By putting the information on a shared ledger, it can be easily made accessible and visible on demand as needed. Because it is tamper-proof, we can remove many existing points of corruption and the associated need for regulation. Likewise, it is made secure by distributed networks without a single point of failure and continuously synchronized across all nodes to create a single source of truth for all users. One of the key technology innovations of second-generation blockchains has been the development of what are called smart contracts. Smart contracts are computer code that are stored inside of a blockchain, which encode contractual agreements. Smart contracts are self-executing, with the terms of the agreement or operation directly written into lines of code, stored and executed on the blockchain computer. A contract, in the traditional sense, is a binding agreement between two or more parties to do or not do something. Each party must trust the other parties to fulfill their side of the obligation. They are a written or spoken agreement that is intended to be enforced by law. A multiplicity of different contractual agreements form the institutional foundations to our modern society and economy, which have evolved since ancient times. If we think about something as seemingly simple as a cafe serving a cup of coffee, we will see that this process is really enabled by a massive amount of contractual agreements between different parties that enable them to cooperate in delivering that outcome. Contracts between employees and employer of the coffee shop, contracts that provide workers with health coverage, contracts that ensure the coffee shop, contracts between suppliers along the supply chain, contracts between property owner and tenant, etc. Our economies are powered by a massively complex set of contractual agreements that are currently created and enforced by centralized organizations like insurance companies and banks, which themselves are supported by the ultimate centralized authority in the system, the nation-state's institutions. Our societies and economies are almost completely dependent upon third-party organizations to maintain and enforce those contractual agreements. Smart contracts feature these same kind of agreements to act or not act, but they remove the need for the trusted third party between members involved in the contract. This is because a smart contract is both defined by the computer code and executed or enforced by the code itself, automatically without discretion. As such, blockchains and smart contract technology can remove the reliance on centralized systems and enable people to create their own contractual agreements that can be automatically enforced and executed by the computer code. These smart contracts are decentralized in that they do not subsist on a single centralized server, but are distributed and self-executing across a network of nodes. This means that untrusted parties can transact with each other in a much more fluid fashion without depending upon third parties to initiate and maintain the rules of the transaction. Likewise, smart contracts enable autonomy between members, meaning that after it is launched and running, a contract and its initiating agents need not be in further contact. One illustration of this concept is a vending machine. Unlike a person, a vending machine operates algorithmically. You provide the source input of money and product selection, which the machine takes as input and simply executes on a rule automatically to produce the pre-specified output. The same instruction set will be followed every time in every case. When you deposit money and make a selection, the item is released. There is no possibility of the machine not wanting to or not feeling like complying with the contract, or only partially complying, as long as it's functional. As another example, we can think about a situation where 4 people pool their money to make a joint investment that will return interest to them. A smart contract could be programmed on the blockchain to take any interest that is created, divide it into 4, and send each amount to the corresponding wallets of the different stakeholders. A smart contract is then really just an account on the blockchain that is controlled by code instead of by a user. Because it's on the blockchain, it is immutable. That means the code cannot be changed, and thus all participants in this investment can be assured that they will get their fair share automatically. The code dictates how the process will take place, and no individual has the power to change it. No individual, no organization, no government can censor, alter, or manipulate the contract. In this respect, it's often said that code is law, in the sense that the code will execute no matter what. Of course, computer code has been for a while now acting as the law. For example, as services have gone online, we're increasingly faced with web forms that strictly control what inputs are allowed. If you want to buy an item on iTunes USA, then you'll have to have a credit card with a US address. The system will auto-enforce this by not letting you complete the purchase with an incorrect address. As another example, a logistics company could use smart contracts to execute code that says, if I receive cash on delivery at this location, then trigger a supplier request to stock a new item, since the existing item was just delivered. A combination of smart contracts with blockchain encoded property gives us the idea of smart property. Smart property is simply property whose ownership is controlled via blockchain encoded contractual agreements. For example, a pre-established smart contract could automatically transfer the ownership of a vehicle title from the holding company to the individual owner when all the loan installments have been cleared. The key idea of smart property is controlling ownership and access to an asset by having it registered as a digital asset on the ledger and connecting that to a smart contract. In some cases, physical world hard assets could quite literally be controlled via the blockchain. One example of such an IoT blockchain system is Slockit, a door lock that is connected to a smart contract on the blockchain, which controls when and who can open the lock. This enables anyone to rent, sell, or share their property without need of a middleman. With such innovations, parking spots can be subletted on demand. Airbnb accommodation could become fully automated. Or someone with 20 bikes in Bangladesh could rent them out. With smart contract locks, the bike could shut itself off if it is not being paid for, or if it's stolen, then there could be an automatic deposit system. Or likewise, if the person wanted, they could simply pay a certain price to purchase the bike at any time. Like all algorithms, smart contracts require input values and only act if certain predefined conditions are met. When a particular value is reached, the smart contract changes its state and executes the programmatically predefined algorithms, automatically triggering an event on the blockchain. Thus, the workings of the overall contract can only be as good as the inputted data. If false data is inputted to the system, then false results will be outputted. Blockchains cannot access data outside of their network and thus require some form of trusted data feed as input to the system, what may be called an oracle. An oracle is a data feed provided by an external service and designed for use in smart contracts on the blockchain. Oracles provide external data and trigger smart contract executions when predefined conditions are met. Such conditions could be any data like weather temperature, the quantity of items in stock, the completion of a successful payment, changes in the prices on the stock market, etc. An oracle, in the context of blockchains and smart contracts, is then an agent that finds and verifies real-world occurrences and provides this information to a blockchain to be used by smart contracts. Oracles are third-party services which are not part of the blockchain consensus mechanism, thus whether it be a news feed, website, or a sensor, the source of information needs to be trustworthy. As an example, we could think of an online betting platform based on the blockchain that uses smart contracts to automatically execute payouts to people who have placed bets on sports matches. The smart contract system would then have to be connected to a trusted oracle to provide it with the score of the matches. As of present, this oracle would likely have to be associated with some trusted third-party centralized organization like a sports channel or Bloomberg for stock prices. However, in the future, through datafication and IoT pervasive sensing, this might also be automated given the use of advanced analytics, using automated oracles that draw data from a myriad of sources and complex analytics to find cross-correlations that provide a statistical assurance that, for example, a given event occurred or did not occur. The advantages of smart contracts are numerous. Firstly, they are automatic, which could remove the time and costs associated with managing and enforcing them, making them more efficient as they can be cheaper and faster to run. Through this form of automation, a much greater amount of exchange could take place that otherwise would have never happened. In such a way, we can see how distributed ledgers and smart contracts are a key part in enabling a true services economy, where ownership is displaced by temporary usage through the on-demand provisioning of services. Secondly, they can reduce corruption, as code is both transparent in its workings and automatically executed. This leaves little room for individuals or organizations to alter it to their advantage. Thirdly, they can reduce dependency upon centralized organizations, as people may be able to set up their own contractual agreements peer-to-peer, thus limiting the arbitrary power of centralized organizations. Lastly, they can also deliver certainty, as smart contracts guarantee a very specific set of outcomes that are predetermined beforehand, enabling all parties to know exactly what will happen. But herein also lies some of their limitations. By automating the execution of a contract, they are dependent upon formal rules with well-specified inputs and leave little room for a multiplicity of eventualities where the rules may need to be slightly altered because of unforeseen circumstances. For example, a car that's being used on demand that operates through a smart contract may simply shut the user out if they have not paid their bill, and would take little account of the fact that it may be a life or death emergency usage. In the real world, many unpredictable and unforeseen events do occur, and rules sometimes need to be flexible and adaptable to accommodate. And this is one advantage of having human oversight, as people are much more capable at judging such circumstances and responding appropriately to complex unforeseen eventualities. So the degree to which we can automate contracts is relative to the kind of environment that it's being operated in, and in more complex situations there will often need to be some form of governing body to intervene when needed, and this creates new complications surrounding governance that are still yet to be figured out. The advent of the Ethereum platform in 2015 has worked to provide a virtual computing infrastructure for running applications on the blockchain. This new form of program is called a distributed application, or dApp for short. Ethereum was the first developer platform for building distributed applications. It was a foundational, general-purpose, blockchain-based platform that is a Turing-complete virtual machine, meaning that it can run any computer code. Although Ethereum was the first and still the largest platform for building distributed applications, there are now others such as Blockstack or EOS, all of which provide the underlying infrastructure for building dApps. Our working definition of a dApp is an application that runs on a network in a distributed fashion, with participant information securely protected and operations executed in a decentralized fashion across a network of nodes. dApps use open source code, operate autonomously with data and records cryptographically stored on a blockchain. On a technical level, a dApp is very much similar to a normal web application, except unlike with a normal web app where the back-end code is running on a centralized server, a dApp has its code running on a distributed peer-to-peer network. A dApp can have front-end code and user interfaces written in any language, just like a normal app. As such, dApps will often look and feel very much like regular apps, and people will soon be using them in the coming decade without even realizing it. Like all apps, dApps perform specific functions, whereas Bitcoin is a decentralized value exchange. A decentralized application aims to achieve functionality beyond transactions that merely exchange value. Many types of decentralized apps are starting to emerge as the underlying technology continues to progress. Already, we can see many dApps that present alternatives to the existing popular web applications. Probably the most successful dApp to date is Steemit. Steemit is a blogging and social networking website on top of the Steemit blockchain database. The general concept is very similar to other blogging websites or social news sites like Reddit, but the text content is saved in a blockchain. Using a blockchain enables rewarding comments and posts with secure tokens of value. In this way, users can earn currencies for their posts and comments. Likewise, for existing marketplace applications like eBay and Craigslist, we have the decentralized version, OpenBazaar. OpenBazaar is an open source project developing a protocol for e-commerce transactions in a fully decentralized marketplace. Because the application connects people directly via a peer-to-peer network, it costs nothing to download and use it. Unlike sites like eBay or Amazon, there are no fees to list items, and no fees when an item is sold. OpenBazaar is not a company like eBay, but an open source project. Each user contributes to the network equally and is in control of their own storage and private data. Another example is Storj, which is a decentralized cloud storage application similar to Dropbox. Storj is based on blockchain technology and peer-to-peer protocols to provide a secure, private, and efficient cloud storage system. The application incentivizes storage providers and connects them with those who require it. Each file saved on the application is shredded, encrypted, and spread across the network until you're ready to use it again. The keys to the database remain with the owners, meaning the data is not accessible by a centralized cloud provider. There are many other examples of dApps, but the general concept can be applied to any area that requires secure records and benefits from decentralization. These applications are automated, which means they can operate at very low or even zero cost. Because of this, dApps may be used to disrupt the existing platform economy, as whole platforms like Uber or Airbnb may eventually be converted into dApps that run automatically without the need for the centralized platform. The advantages of dApps is that they're fully automated, have superior fault tolerance and trustless execution. these decentralized apps potentially represent the next generation of computing. Because the blockchain is a secure system that enables a trusted network, it's often described as a value exchange protocol. In this respect, people often say that what the web did for the exchange of information, the blockchain will do for the exchange of value. Just as the web revolutionized the use and exchange of information within society, disrupting whole industries based upon the centralization of information, so too the blockchain is set to do the same for the recording and exchanging of all forms of quantifiable value. This idea of value lies at the heart of the blockchain. If there is no value involved in the process, then there is no need for trust and no need to use the blockchain. The vision of the Internet of Value is for any quantum of value to be exchanged as quickly and as fluidly as multimedia is today on the web. Although multimedia can move around the world almost instantaneously, a single payment from one country to another is slow, expensive and unreliable, often taking days and involving numerous intermediary third parties to validate and process transactions at a significant cost. Thus it is no accident that the first widespread use of the blockchain was for currencies, because it is the most immediate and obvious source of quantified value within society. However, to truly understand the revolutionary potential of this technology is to appreciate how value and its exchange influences and regulates almost all aspects of human affairs. As a consequence, the control of how value gets defined, measured and exchanged is a key source of power and control within society and has been since the origins of civilization. Today, value of almost any kind is defined, quantified and regulated by centralized organizations, whether this is a national government creating their own currency, or one's role within a hierarchy defining one's economic status, or the branded clothing that we wear to signal to others our social status and value in society. However, the move into the network society shifts the locus of organization from closed institutions to individuals and networks. Blockchain technology is a key element enabling this process. By creating a shared ledger where people can own their own data, it also enables a shift in the locus of value within economy to the individual in networks. In a world of limited connectivity, limited transparency, and limited peer-to-peer trust, it was necessary to have third-party institutions to define, quantify, and authenticate sources of value within society and economy. But in a world of pervasive peer-to-peer connectivity, transparency, and trusted, low-cost, automated networks, value can be defined through a negotiation between peers within distributed networks. The rise of digital currencies are but one such example of this. The surprising thing for a lot of people is that most major currencies like the dollar, yen and euro aren't backed by anything. They're just pieces of metal, paper and entries in a bank account that get their value from everyone simply believing that they have value and accepting them as a medium of exchange, and that's all that's really necessary. Currencies and money work a little bit like languages. They are subject to network effects to give them value. The more people who agree to and understand a language, the more valuable that specific language has as a form of communications. Dollars, renminbi, euros and bitcoins have no intrinsic value. They're all social protocols, and they merely represent a way of supporting the value flows between individuals. In the past, because of low levels of trusted peer connectivity, we required centralized institutions like governments and banks to get these value exchange networks started, to support them, regulate them, and maintain them, and this gave those organizations a lot of power. This is a critical aspect that the internet and the blockchain are changing. The blockchain enables us to create trusted and automated peer networks of exchange, which greatly strengthens the capacities of people to negotiate and define value via direct peer-to-peer exchanges. People can now set up their own currencies with the value of the currency depending simply on what others are willing to pay for it via an automated peer-to-peer network exchange. But the Internet of Value is more than just currencies, because value is of course a much broader concept than just pure economic utility. In talking about the Internet of Value, it's important to recognize that on a societal level, we're moving into a post-industrial services economy. The traditional conception of what society values is being revisited as a new set of societal and environmental factors re-enter the equation. People are less and less content with the traditional concept of GDP as the sole metric for how well they're doing, and more demanding actual quality of life, which of course engenders a broader spectrum of values beyond economic utility. Over the past decades, we've increasingly begun the process of tracking and accounting for different forms of value, whether this is green bonds, social impact bonds, company loyalty schemes, carbon accounting, or a multiplicity of other forms. Put simply, the erosion and loss of social and environmental capital that occurred during the industrial age is generating a recognition and growing awareness to their value. Metrics for how well a society is doing increasingly take account of many more environmental and social parameters in combination with GDP. Along with this recognition to the importance of different forms of value comes also the technical means to quantify and exchange them. Through the process of datafication, information technology lets us measure, track and exchange ever more types of value at ever smaller increments. Likes on Facebook, people's attention, carbon emissions, etc. With the rise of big data and IoT, we'll be quantifying and ascribing value to almost everything, and the blockchain will provide the networked infrastructure for tracking and exchanging all these micro and macro quanta of value. This shift from the narrow form of economic value that dominated in the industrial age to a broader spectrum of values that emerges within a post-industrial society is enabled by the distributed ledger system that supports what we call token economies, wherein we can define a token as a measure of any form of value and then build an economy around that. Token economies and the Internet of Value build upon the current expansion of digital markets brought about by the rise of the platform economy. Over the past decades, with Web 2.0, we've begun the process of expanding markets to more and more spheres of life that were previously organized via centralized coordination. After only 10 years or so of this process, the biggest accommodation service in the world is no longer a centralized organization like the Hilton, it's now an online market. The same is true for the taxi industry, the same is true for commerce. With 10 million merchants and 440 million active users, the Alibaba network is now reported as the largest retailer in the world, after just 19 years of existence. Markets are complex. They typically require the aggregation of large amounts of information and peer-to-peer interactions. Without the technology, it is much more viable to achieve coordination via a centralized hierarchical model. But as we come to quantify and account for more and more areas of life, blockchain-based networks will expand the capacities of plug-and-play markets to all spheres of activity: social, economic, technological, and environmental. The Internet of Value will function as the infrastructure to the emergence of the services economy, which is currently taking place within post-industrial economies. The move into a services economy results in the conversion of industrial age products into services, whereas the product-based economic paradigm was about the production and consumption of more products as measured by GDP. A services economy is about value delivered. A service is an exchange of value. You don't get the product, you just get its function and the value that it delivers. As such, all spheres of economy become redefined away from the static conception of units of products towards the more fluid exchange of value. You don't buy a lift to put in your office building, you get it as a service, paying only for the functional value it delivers. In some offices now, they don't even buy the carpets on the floor. The function of the carpet is delivered as a service, and they pay only for the value that's exchanged. The blockchain is a key infrastructure enabling this services economy, as it requires a very fluid, dynamic, and automatic tracking and exchange of value. Smart property and smart contracts will form the technological infrastructure powering the services economy, as they operate within large peer networks, automatically allocating resources and processing the financial debits and credits of value exchanges behind the scenes. This huge shift in our economy lets us reconceptualize every industry to really question what is the actual value that it delivers, and then reconstruct it by building token markets around that value, where anyone can participate in the delivery of the service. With Web 2.0 and the platform economy, we extended the capacities of markets so that many more people could participate, as exemplified by Uber, enabling anyone to operate as a driver. However, these markets were centralized around the platform operators, and they were dependent on traditional currency systems and the financial system for processing transactions. In Web 3.0, blockchain applications will function as distributed, automatic, plug-and-play markets, where extremely small increments of value can be exchanged directly peer-to-peer with very high levels of fluidity. When this is coupled with IoT and data analytics, we'll be able to track the real value that things deliver, which will help us to make the much needed move from our product-based economies to an outcomes economy that better reflects the underlying value being created and exchanged.
With the ongoing revolution in information technology, our economic systems of organization are being transformed and disrupted by the rise of information networks. It started with the advent of the personal computer, World Wide Web, and with the rise of online platforms, the disruptive power of information networks to reshape economic organization became ever more apparent. Today, this process of economic transformation continues with a new set of technologies, as we are currently in the process of remaking the technology stack of the Internet, building what is called Web 3.0, a primary component of which is the blockchain. The defining feature of this next stage of economic development is that it decentralizes our economy and shifts operations to global information-based networks like never before. This distributed Internet technology stack that is currently being built enables a network of computers to maintain a collective database of value ownership and exchanges via Internet protocols. This bookkeeping is neither closed nor the control of one party. Rather, it is public and available in one digital ledger, which is distributed across the network. The most mature example of this is what we call the blockchain. In the blockchain, all transactions are logged, including information on the date, time, participants, and amount of every single transaction. On the basis of sophisticated mathematical principles, the transactions are verified by the so-called miners who run the computing infrastructure required to maintain the ledgers. The technology of Web 3.0 enables a new form of decentralized economy, as it removes the dependency on a centralized authority for managing the network, instead replacing it with a distributed consensus model managed by many. This shared, securely encrypted database enables trustless, peer-to-peer interactions via new Internet protocols. People can begin to set up their own networks for coordination and direct exchanges of value peer-to-peer, and it enables the rules of these transactions to be automated in new ways. At the heart of this system is the distributed ledger, which records the exchanges of value. These distributed ledgers can account for and validate the exchange of any form of value. It may be a currency, it may be property, it may be a kilowatt-hour of energy, the usage of a parking spot, the number of followers a person has on social media. These distributed ledgers provide the infrastructure for building token economies. A token is simply a quantified unit of value. Tokens are both generic and fungible. It is generic in that it can be used to define any form of value, and it is fungible, meaning it is exchangeable between different specific forms of value. Traditional monetary currencies are not fully fungible, as there are many circumstances when one cannot exchange a monetary currency for other forms of value. For example, likes on social media may have a certain value, but typically cannot be directly exchanged for monetary currencies. A token differs from our traditional monetary currency in that it is more generic. Our existing currencies define a particular type of monetary value, what we call utility, which is based upon the economic logic of the industrial economy, while tokens, because they are more generic, can define a broader set of values, social capital, natural capital, or cultural capital. For example, natural capital is the integrity of an ecosystem that enables it to function and provide ecosystems services to people. In our traditional economic model, we only quantify and account for the services that the ecosystem delivers, such as food, water, materials, etc. However, we do not account for the integrity of the ecosystem that enables it to function. The generic nature of the token means it can be used to account for values such as this natural capital. The capacity to differentiate between different forms of value is made possible by the programmability of token units. Because tokens are digital, they are also programmable, which enables one to specify certain rules for that token and have those rules executed when it is exchanged, thus enabling certain constraints or possibilities in its usage. One can specify that a certain token is only spendable under certain terms, or specify how it can be converted. For example, one could program the token so that it cannot be exchanged for diamonds that are mined in a particular location of the world known for its use of slave labor. In this way, the token is not just a unit of utility, but also expresses social values. Likewise, one could create a healthcare allowance in dollars or euros that could be programmed on the blockchain so that it can only be used to pay for healthcare at certified parties. Automating these measures leads to a considerable decrease in bureaucracy. This programmable token system works to shift our economies from a single value model to a multi-value model. They create many different types of value and economies, but still retain the possibility for exchange between them. The distributed web is the convergence of the economic market system with information technology that enables us to convert traditional organizations into distributed markets based on tokens. Tokens define whatever is of value within that organization, and the market system is used as a distributed coordination mechanism for managing and growing that resource. By creating an expanded definition of value and converting closed organizations into open markets, this means that we can vastly expand the scope and capacities of the economy. The provisioning of services within the economy no longer becomes dependent upon a limited number of centralized organizations acting for profit, but instead, anyone can now provide the service via these open protocols. This means we can harness the resources of the many in a distributed fashion instead of being dependent upon a few. Likewise, the token economy can harness the motives of individuals not just for financial rewards, but for a multiplicity of values. To illustrate how this works, let's think about the service of cloud data storage. Currently, this is provided by a limited number of enterprises like Amazon and Microsoft. These centralized organizations have huge data centers, but still, those data centers are only a very small fraction of the storage capacity in the world. Most of the storage is in the personal computing devices of end users, and most of that is not being used. Filecoin is one organization that works to create a distributed token economy for this storage. Filecoin is a decentralized storage network that turns cloud storage into an algorithmic market. The market runs on a blockchain with a native protocol token, also called Filecoin, which miners earn by providing storage to clients. Conversely, clients spend Filecoins hiring miners to store or distribute data. The sum of all these computers that are coordinated through an automatic market system on the blockchain can provide a much larger, more resilient system than the centralized model while reducing redundancy and inefficiencies in the overall system. It also pushes the provision of the service out to the location where it is demanded, as people are connecting peer-to-peer locally instead of going to the centralized server that may be on the other side of the planet. Tokens such as filecoins can be exchanged for other currencies, or members can hold on to their tokens whose value may appreciate as the networks grow over time. This illustrates a very interesting aspect to tokens. Anyone who uses the system is also an investor in the system. Thus, tokens merge investment capital and liquid exchange capital in new ways. In the traditional capitalist model, we have a divide between owners of capital and workers, a divide between a more fixed investment capital and liquid exchange currencies. The shares in a company are not the same thing as what people get paid with for working in that enterprise and use for everyday exchanges in the market. This creates the notorious divide within the industrial economy described by Karl Marx, between the capitalists that make money off their investments and the workers that have to stay selling their labor for money without ownership. Tokens represent both the inherent value of the community, which is its capital investment, and they are also units of exchange within that ecosystem. The founders of the project issue a number of tokens at inception and sell those. For someone to use the system, they have to buy the tokens. In so doing, they become part investors in the project, but they also use those same tokens to make exchanges within the market. Thus, the people creating the value in the ecosystem are also getting paid in tokens, meaning the workers that are creating the value through their work also have ownership within the organization. In the traditional utility-based exchange of cash, people have no ownership in the organization. They just try to make money, and this can create divides between the owners and the users. The token system works to better align the incentives of the individuals with the overall system because the value of the tokens they earn is also dependent upon the value of the whole. When you are working for a token network, you are both working for yourself and for the whole organization as the two become more aligned, unlike the traditional divide between capitalist and worker. The token system enables networks to overcome the chicken and egg problem. If you are the first user of a network like eBay, then the value would be very low. Thus, it is difficult to get the network started because it has to reach a critical mass before it will be of value to the users. This means that it may require a large investment to create a network. The Silicon Valley model worked by having large initial venture capital backing that enables them to overcome this. But it means that most networks don't get off the ground, and that once a network reaches scale and has value, it becomes dominant and very difficult to compete with, resulting in a lock-in effect and making it easy for large incumbent organizations to become extractive over time. It also means that those who founded the organization win big time. If the network takes off, it creates a winner-takes-all dynamic with most people losing because of the threshold. The token system extends the benefits of being an early adopter of a new network to all the users and thus helps to solve this issue. It does this by issuing tokens for anyone to purchase at the beginning of the project. As the project grows, the tokens come to have greater value for all of the holders. This also works to make the users of the network promoters of that organization because as it grows, the tokens that they hold become more valuable. It incentivizes people to join networks early so as to gain the benefits of the increase in their token value as it grows, which reduces the problem of thresholds. With this, technology companies no longer have to go to traditional capital markets through an initial public offering of shares in the company in exchange for money. But instead, they simply sell tokens directly on the internet to raise initial capital for the project in what is called an initial coin offering, or ICO. This means that founders can monetize their networks directly by simply holding their tokens and making the network useful. To date, we have had an internet patched onto the side of an economy operated through the many centralized organizations of the industrial age, creating a strong contradiction between the underlying technology and the institutional arrangements. The distributed web will work to transform this by merging information networks and economic organization as the flow of information and economic value becomes one. This will greatly reduce our dependency on centralized organizations expanding markets as systems of organization. The global market economy will become available to the many through small distributed peer-to-peer interactions running through web protocols as the decentralized internet takes us a step further into the networked economy.